one is the final part that we're going to do on the unit, which is body defences. Now, this particular component of the unit is all about what we call blood clotting, hemostasis, okay? So this is the final thing that you're going to do on this particular unit for me, which is all about body defences, how blood actually clots, okay? Don't forget, this is a PowerPoint, it's on Teams, the opening slide looks just like this. So, in this particular lesson, we're going to look at the first part of this PowerPoint. We're going to split it into two. We're going to look at the main stages in the formation and the main players involved in blood clotting. And that's going to be the first part of this particular tutorial. We're going to get to that particular point there, okay? So the first part is going to go through the major stages in blood clotting. Right, let's press on. Everybody excited? I hope you are. Now, it's a complicated procedure, and we could really spend an awful lot of time on this, and some people do. However, given the size of the unit that we've got on body defences, I'm kind of going to give you the highlights of what's involved in actual blood clotting. Okay? So, the first most important thing to remember with blood clotting is it is a 3-stage process. And I need you to tell me in the work that you are doing, is it a 3-stage process? Number one, as a highlight, and we're going to go into these in a little bit more depth. Number one, narrowing, also called vasoconstriction. In other words, when you get an injury to a blood vessel, the first stage of stopping all the blood from leaking out is it is going to narrow. It is going to get narrower. Stage 2, the formation of what we call the platelet plug, which is the activation of small, like semi-fragments and particles that you've got in your bloodstream, which we call platelets, that are going to form a plug over the hole. Again, a very temporary construction to reduce the amount of blood that's actually flowing out. And finally, stage 3, we are going to move to the fibrin meshwork, okay? Fibrin is almost like a long chain of things which is going to tie everything together and form a meshwork around the hole, which is a more semi-secure kind of temporary repair until the actual blood vessel can repair itself with proper cells underneath. Because don't forget, this process, right the way from the beginning to the end, has to be quick because you want to limit the amount of blood that's actually leaking out. But let's not forget, it is also temporary. It's a temporary repair to stop blood from leaking out of the blood vessel, okay? It's not a permanent repair, it's a temporary repair. So, nice kind of diagram, a useful one for you to draw, a useful one for you to lift out from the internet as long as you reference it. And I've just lifted this one out because quite clearly it shows you visually, which you might want to use in the work you're doing, it quite clearly shows you this is the sequence that we go through. There's been damage to a blood vessel. Stage 1, vasoconstriction, the blood vessel gets narrowed. Stage 2, we get this platelet plug forming, okay? A temporary repair stopping blood from leaking out. Stage 3, a more semi-permanent repair, which has greater structural integrity, that basically means that blood should not leak out of that. But let's not forget, as I have mentioned, all of these are temporary. They are not replacing the cells that should be there, they are merely blocking up the hole. In the same way that maybe if you've got a pothole in the road, for example, and you're going to resurface the road, but right now you can't do that, you're just going to fill in the pothole, okay? This is kind of filling in the hole, this is kind of filling in the pothole. Okay, so let's look at stage 1, vasoconstriction. We narrow the site of the blood vessel where the injury has occurred. Okay? Why do we do it? Kind of self-evident really, guys. We want to limit blood loss. Now this process is controlled, and there are 2 layers of control. There's a general systemic layer of control, because when you injure a blood vessel, you will start to release adrenaline into your blood system, okay? Adrenaline will cause vasoconstriction of a lot of blood vessels. I'm not too interested in that one. So I'm not massively interested in systemic control, although maybe you want to mention it so I know that you're aware that it exists. The one I'm more interested in, the one I want to see you putting into the work that you're doing for me, is this local control. The blood vessel narrows locally because something is released called thromboxane, and it is released from something which is called a platelet, which we'll look at in a second, only when that platelet becomes activated. Thromboxane is what we call a vasoconstrictor, which means it is going to narrow that blood vessel down locally in the area where we have a hole. Okay? So, stage 1, vasoconstriction. Systemic controls are going to narrow a whole load of blood vessels that may be taking blood to the site of where the injury is. But what we're really interested in is this localized level of vasoconstriction, which is effectively produced by platelets releasing thromboxane, which is a vasoconstrictor. This is going to get the area around the hole to squeeze together to reduce blood flow very, very low. So, that's phase 1. Phase 2, cooking on gas. Phase 2, platelets. I introduced those before because I said that they release thromboxane. Kind of makes sense now because the other word for a platelet is a thrombocyte. Now, they are small cellular particles and they are constantly flowing around the blood with your red blood cells. However, whilst they are flowing around, they are kind of really smooth shape. They're kind of like a flying saucer shape, like a disco, like a poppadom, but much smaller. And they kind of retain that really smooth shape until they come into contact with collagen. And especially these collagen fibres that basically surround the outside of every single blood vessel. Even a capillary, which is 1 cell thick, will have a very, very tiny layer of collagen supporting it or around it, okay? Especially the bigger blood vessels, they certainly do. So collagen never really comes into contact with the blood itself. It kind of surrounds the blood vessel, stays on the outside. But when you get an injury, it means for the first time that these platelets are going to be exposed to the basement membrane of a blood vessel. And that's when things really start to change. Because platelets suddenly start to change shape. And in changing shape, they stick to the collagen. And in sticking to the collagen, they also then release those chemicals, the main one of which is thromboxane. So they release thromboxane, which we now know causes narrowing. So they become activated and they narrow the blood vessel. When they become activated, we'll see that they change shape. And when they change shape, they go from a disco to like a poppadom or a disco crisp to an onion bhaji. They change shape though, so they become really stickly and prickly. And because they change shape, it means they can stick together much, much closer, and that they can really like lock together like almost badly fitting pieces of a jigsaw. And they form the platelet plug. This is the first stage in actually really sort of like plugging the hole. Vasoconstriction narrows the amount of blood that is actually going to the area that can get out of the hole, but this actually plugs the hole up. So let's have a look at that. Here are our platelets. Disco, nice and round, okay? Nicely shaped, nice and round, so they don't stick to anything, because you don't want them to stick to anything if nothing's going wrong. But when they reach collagen, so if this were like a collagen layer here, we'll see it better in a second, if this was collagen, then all of a sudden they change shape from this, and they go to this. Now can you see that these kind of look like onion bhajis? They're all kind of squiggly. But can you see how, because they've all got little lines on them and they kind of all interlock together, they form a plug. They literally form together like a little mass, and they will plug the hole that stops blood actually leaking out of the blood vessel. Kind of really cool the way it actually does it. We'll come on to this, but we don't really want these floating off past the site of the injury looking like that, because that might cause us all sorts of problems. We don't want these all stuck together flowing down a blood vessel, because they may block the blood vessel further down. So we'll talk about how we inactivate them. But first of all, there's another diagram I'll show you here which goes through that process. Okay? Let me just go on to this one. No, we'll go back. So, we know that we've got platelets, which are also called thrombocytes. We know that they are nice and round when they are not activated, and we know they change into an onion barge shape, or smaller, when they are actually activated, okay? And they form a plug. And as I've said just before, what we want to make sure is that these do not leave and go past the site of the injury and carry on flowing all the way down the blood vessel where we don't want them to be. So we need them to be inactivated. We need them to be inactivated. We don't want them flowing past the site of the injury. So how does that happen? Well, very cleverly, the normal cells that have not been injured in your blood vessels secrete something which is called prostacyclin. And prostacyclin enters the bloodstream, like a dripping tap type of thing from the cell. And effectively this inhibits platelet activation, which means any activated platelets that flow beyond the site of the injury become deactivated really, really quickly, so they don't cause us a problem. They don't clump. It's really clever. Let's have a look at that. So here we have our blood flow moving this way. Here we have the platelets in our blood. These are not currently activated, so they are nice and smooth, like this. They don't stick together, they're just flowing along like disco. This is the hole that we have, the site of the injury. We already know that this is basically narrowed down to try and reduce blood loss, okay? Because that chemical thromboxane has done that. What we also can see here is this basement membrane. Can you see it here in green? This basement membrane is never normally seen by these platelets. When they see or come into contact with that basic membrane, that's when they change from this lovely smooth shape to this kind of shape, like wild onion barges, okay, all over the place. And because they've got all these different shapes and projections, it means that they can lock together like a really ill-fitting piece of a jigsaw. It is these that basically block that hole. That is the platelet plug. Now, the last thing that we want is for one of these to be floating off past the site of the injury, or even more than one, passing the site of the injury, because these could potentially block this blood vessel lower down. So all the healthy cells in this layer of your blood vessel secrete this thing called prostacyclin, and they release it into the bloodstream. As soon as these activated platelets hit this prostacyclin, which is kind of like a chemical, then effectively they change from that shape and they go back to that shape. No problem. No problemo. Bingo. Disco. So effectively, it all goes back to normal. Really, really clever. Fantastic piece of kit. Okay? So we've done stage 1, and we've kind of done stage 2. Let's look at stage 3. Stage 3 involves something called a polymer called fibrin. Okay? A polymer is simply the word that we use to describe a long chain. Poly meaning many. Okay? So it's a long, long chain. So fibrin is a polymer, a chain. Each individual one of these started off life as a monomer, meaning a single unit, called fibrinogen. Fibrinogen. Okay? So let's think of it like Lego. Okay? Fibrinogen is a single Lego block. Fibrin is a whole chain of blocks all stuck together in a line. Fibrinogen floating around, monomers, single blocks on their own. Fibrin, whole chain of blocks, all in a line, all glued together. The third stage of blood clotting basically changes these single bricks, fibrinogens, into this long polymer called fibrin. And this is that final process that we're going to talk about now. This is the real strength component to stopping blood actually leaking out of the hole. The actual previous stage, where we talked about platelets, is kind of a really temporary, so maybe blood might still be kind of just about leaking out, but this is going to basically seal the whole job off. Okay. So, let's look at this stage. Great slide for you. Lots of writing on it. I'm going to take my time and go through this, and then there's a diagram that follows as well. Okay. So probably some of you are thinking, okay, Derry, so we've got these fibrinogen Lego bricks, and they're going to be somehow converted into fibrin, which is a long chain, and this long chain is basically going to crisscross over the hole and stop any blood from actually leaking out. And you'd be kind of right. And I suppose some of you also might be thinking, how the hell does fibrin get created? What stops this fibrinogen from actually sticking together to form fibrin when we don't actually need it? Because that would be kind of disastrous. What stops fibrinogen from sticking to other fibrinogen monomers is that fibrinogen has a cap on its ends. Now this cap basically stops two fibrinogens from sticking together. So to make them stick together, you're probably kind of thinking, oh, I've kind of got this already, Dave. We need to remove the cap. So somehow we need to take the caps off fibrinogen so that the fibrin monomers can then stick together. So how the hell do we actually get these caps off? Well, to remove the caps, we have an enzyme called thrombin. And thrombin basically removes these caps, converting the inactive fibrinogen into active monomers of fibrin. Now, for this process to work, we then have to glue these active fibrin monomers together. And calcium is basically the glue that holds the fibrin monomers to actually hold them together, okay? Glues them together into a long chain which eventually forms a meshwork, okay? So let's have a look at that. That's a great description, one that you should be using as a D-grade student to basically explain this third and final stage, combined with a diagram that looks like this. Here is our fibrinogen monomer. Monomer meaning a single unit. So here it is. Okay? And here's another one. Okay? They are not stuck together. Along comes this enzyme, we're going to talk about this later, called thrombin. Thrombin takes the caps off fibrinogen, leaving behind fibrin, but it's still not stuck together, so it's still a monomer. In the presence of calcium, which is already in the blood, the calcium acts as a glue, which basically seals the actual monomers of fibrin together to create a chain, which we call a polymer. And now, all of a sudden, we have this fibrin chain, this fibrin polymer. And you can see the chain over here. And the chains basically crisscross all over the hole. Here's the hole. And they crisscross the hole all over the place like this. And in producing this mesh network, they trap red blood cells, they trap those platelets, they trap everything, and this becomes your semi-permanent repair. This is blood tight. Nothing is going to seep out of this. And this then gives the blood vessel time to heal itself. And then we'll talk about, in the later part of this particular tutorial, we'll talk about how the heck we get rid of this, because we don't want this simply falling off like a scab and simply floating its way down a blood vessel. So we'll talk about how we safely remove this. Okay? So here we see a computer-generated image of fibrin as a polymer. These big things here are your red blood cells, and everything that you can see here, which looks like a spider's web, is in fact the polymer fibrin, made up of those individual tiny little fibrinogen monomers. And you can see it kind of acts like a fishing net, trapping all the red blood cells inside, not allowing them to get out. It forms this semi-permanent repair where blood isn't going to seep out anymore, basically closing off the hole in the blood vessel until a more permanent solution is arrived at, meaning that the blood vessel actually heals itself underneath this particular fibrin meshwork. And that's where we're going to leave the first part of this process. So what we've talked about in this little tiny seminar, the first part, is the 3 stages of how we actually seal a hole in a damaged blood vessel. And it's that kind of level of detail and those diagrams that you kind of need to re-show me when you're dealing with this in your assignments brief. I hope that kind of helps you. Don't forget this PowerPoint is on Teams as well. So have a good look at it. Any questions, ask me in the sessions.